take up here, so we've got to this stage where we're talking about collisions, and there's two types of collisions, as I think we mentioned last time. There's basically inelastic, meaning not elastic, and there's elastic. And elastic means that not just momentum is conserved, but kinetic energy is conserved. There's no energy lost through friction, say, to thermal energy. And let's put this timer on for 50 minutes. And so good examples of elastic collisions would be atomic particles tend to interact elastically. To some extent, air molecules, to a large extent, air molecules colliding in the air. You don't hear that roar you would do with a car crash. You don't hear the bang. You don't hear anything, and that's because they're, a reasonable approximation to elasticity. If you go and play pool or snooker, you don't hear a loud crash when the balls hit each other. So that's an approximation to it. On the other examples, car crash, you hear the sound and the fury of the car crash. That energy has to be paid for, and it comes from mechanical energy. So your kinetic energy of the system before the two cars is more than the kinetic energy of the system afterwards, because you paid for all that sound and that heat and all that. And there's a special case of a inelastic collision, and that is not only do you have a car crash, but the two things stick together so that they travel with the same speed afterwards as they did before, as each other, not as they did before, but as each other. And that's a special case. It's actually the opposite of an explosion if you think about it. It's like if two objects coming together as one is the opposite of one object splitting into two. And so they like to dress up this question a little bit. There's a classic question of, I'm in a spacewalk and my spaceship is 20 feet to the side of me, and my little jet pack that drives me around, little air compressor pack, is used up, and I don't have a line, so I can't pull myself back in. So how on earth can I get back to the spaceship having fixed my whatever it was, And the answer is it's the opposite to an inelastic collision, a perfectly inelastic collision. So there's me and my backpack, and we have the same velocity before, and then I throw the backpack away, and because the two of us had zero momentum to begin with, we got to have zero momentum afterwards. So my positive momentum as I go towards the spaceship is balanced by the negative momentum of what I throw away. And so you can get this thing where you can, if you're prepared to sacrifice part of the mass of the system, you can get motion. You get the same thing if you get into a canoe and you just, like, it's in a lake, and you just decide to get up and walk to the other end of the canoe. If you really looked at what happened, is it's not like, you walk across the canoe. As you walk, the canoe moves backwards. It's like the center of mass stays the same. You're over at one side to begin with. As you walk to the other side, the system adjusts. So your forward motion is balanced by the backwards motion of the canoe. So there's some special cases you can play with. But by and large, there's basically two schools. There's the inelastic collision and there's the elastic collision. In inelastic collisions, because kinetic energy is not conserved, then all you can say is that momentum is conserved. That's the total momentum before is balanced by the total momentum afterwards. And if these two guys actually stick together, then the total momentum afterwards is m1 times v final plus m2 times v final. Frankly, I'm not even sure it's worth a second equation. It's just a special case of the first equation. It's like, if you just do this first equation, you recognize that v1 is the same as v2, you can do it. You don't really need a special equation for it. And then on the other side, when those cases where we have no kinetic energy is converted into heat or sound or whatever, then we still have conservation of momentum, but because none of that energy is lost to heat or sound, we also have conservation of kinetic energy. And it would be tempting to say a half m1 v1 initial squared plus 1/2 m2 times v2 initial squared is equal to a half m1 v1 final squared plus 1/2 m2 v2 final squared. I'm just taking this top line and I'm just converting it into a conservation of energy line, yeah? Two objects before, same two objects afterwards, different velocities, you know. The problem with this is that trying to combine those two equations in a kind of like a simultaneous equation system is a total pain. You can try it, people do try it, and it's just like it's mathematically it takes a lot of work in to try and sort out what's going on. And then someone came along with an alternative, which is this, which basically says for elastic collisions, the difference in the velocities before the collision, v1 minus v2 before, is equal to the negative of the difference between the velocities after the collision, v1 final minus v2 final. And that's a new thing to remember, and it really saves you a lot of work. So that really is worth remembering. When I was a student, I was a bit naive, so I remember hoping that I got a elastic collision because there were two equations. So if one didn't work, I could always try the other one. And you know, now I'm older and sadder and wiser. I know that two equations means two unknowns and simultaneous equations. You know, that's what it means. The reality is you're going to need both equations. So, well. So let's do some. So a 7 kilogram. Got to find my pen as usual. Oh, my pen has decided to. Man, the pen's getting tired too. Okay, let's unplug and plug. I know. Let's go down here. We're back. Okay. So a 7 kilogram. So I like to draw my little visualization. 7 kilogram object with a speed 4 meters per second. And it's to the right, so we'll call it positive. Collides with an inelastically. Oh, okay. So it's telling me it's inelastic with a 2 kilogram particle that has a velocity of minus 3 meters per second. And then we have our collision. And then after the collision, the 7 kilogram particle has a velocity of, plus 2 meters per second. And what is the velocity of the 2 kilogram particle? So I can call it just V. There's only one unknown velocity, so I'll call it V. So on the left hand we have the before, on the left hand we have the afterwards. And the principle is the momentum initial is equal to the momentum final. Yeah, that's the principle. So we say 7 times plus 4 plus 2 times minus 3 gives me 7 times plus 2 added to 2 times V. So that momentum added to that momentum before is equal to that momentum added to that momentum afterwards. So that's going to be 28 plus minus 6 gives me 14 plus 2V. So rearranging, let's put the, I can put down equals. I'm showing the arrows, but it can be equals. Mathematically, it's equal. So I go, well, V is equal to 28. Let's just leave it alone for the minute, and I'll do the math in a minute. So let's have a look. That's going to be minus 14 divided by 2. So I took the 14 to the other side, became a minus sign, and then I divided the whole thing by the 2. So I get V is equal to 28 minus 6 is going to be 22, minus 14 is going to be 12, that's going to be 8 over 2, which equals plus 4 meters per second. Is that one of my choices? I wish I'd put down plus 4 there, because, you know, it's a sign. I wish I'd put that in, but I didn't, you know. Where's that guy? Not so bad, yeah? It's just momentum before equals momentum afterwards. No big deal. 3 kilogram particle with a velocity of 3 meters per second collides perfectly inelastically. So there's my 3 kilogram meters, and I used plus 3, that's interesting, plus 3 meters per second. Collides perfectly inelastically with a 2 kilogram particle with a velocity of minus 4 meters per second. And that goes to, what's the velocity of the combined particle? Oh, I'm being really kind there. I'm really emphasizing it. As long as I tell you it's a perfectly inelastic collision, or the two stick together, as long as there's some indication of that, then I could say to you, what's the velocity of the combined mass? I could say, what's the velocity of the 2 kilogram particle? What's the velocity of the 3 kilogram particle? Because if the combined mass has a speed of 10 meters per second, then the 2 kilogram particle has a speed of 10 meters per second, because it's part of the combination. So I don't have to be so clear, you know, about it's an inelastic collision. Oh, and by the way, if you miss that, the 2 particles stick together. I can be kind of like, you know, do you get what inelastic collision is? By the way, I'm not above on a test saying, you know, what's conserved in an inelastic collision, and then you have to decide, well, is it just momentum, or is it momentum and kinetic energy? You know, so a nice definition like that, I think, is fine. So this is going to be combined velocity of V. So I get my P initial is equal to my P final. And again, this is going to be fine. It's going to be 3 times plus 3 added to 2 times minus 4. And that is going to be, and I like to put down 3 plus 2 so that visually I know I did add them together. It's one of those, like, you know, this is what you did, Bonaquisti. You added them together times V. So that's going to be 9 plus minus 8 is equal to 5V. So V is equal to 9 minus 8 over 5, which equals 1 over 5. V is equal to plus 0.2 meters per second. And I wish, again, I'd put down signs on this, because it is a direction. You know, it's not the speed I'm asking for. And it did go in the positive direction. It could have gone negative if I'd made that 2 kilogram mass a bit faster, rather than slowing down when it was a combination. It could have even gone the other way. The combination could have pushed, if you think about it, in this case, the 3 pushed the 2 backwards, yeah? The 2 had a negative velocity, now it's got a positive velocity. So the 3 has pushed the 2 backwards. It's overwhelmed it, because it had more momentum, because it was 3 times 3, which is 9, rather than 2 times 4, which is 8. So the particle with the most momentum before is the 3 kilogram, and it's going towards the right. So the combination is going to go towards the right. But I could have just as easily changed that and given this 2 kilogram a bit more mass, or a bit more velocity to give it more momentum. Then the momentum's pushing to the left more, and then the 3 kilogram would have been pushed to the left, as the 2 kilogram would have been, etc. So it's not always going to be a positive answer that comes out. And then a 2 kilogram particle with a velocity of 5, so this is 2, and this is a velocity of 5 meters per second, positive, collides elastically. Oh, okay. with a 4 kilogram with a velocity of -3. So that's the before. And then what happens afterwards? Well, they don't stick together. So that's going to be a V, let's call it a V2 final. And this is going to be a V4 final. Because of the two masses, we'll call it, V2 meaning V for the 2 kilogram and V4 meaning V for the 4 kilogram. Two unknowns. So the first thing I'm going to say is that P initial is equal to P final. So I look and I say, well, it's going to be 2 times plus 5 added to 4 times minus 3. And that equals 2V2 final plus 4V4 final. So let's just do one more step. So that's going to be 10. And that's going to be minus 12. 10 minus 12 is minus 2 is equal to 2V2 final plus 4V4 final. So that's 10 and that's minus 12, so that's going to be minus 2 on that left hand side. Two unknowns again, I've got to solve it, and I could try using my kinetic energy, but let's just do this new equation. It's the difference in the velocities before. So V1, let's call it V2 initial, minus V4 initial is equal to, keep them in the same order, V2 final minus V4 final. So just keep the two velocity numbers in the same order, but put the negative sign in front of the right hand side. And look up here and I go, well, this is going to be plus 5 minus, and for 4 is minus 3, and this is going to equal, I don't have any numbers to put in here, but let's get rid of this negative sign. So it's going to go V4 final minus V2 final. That's kind of nicer. So 5 minus, oh, that's 8. 8 is equal to V4 final minus V2 final. Yeah, I got two equations and two unknowns. Now, there's a little bit of experience here, and what I know is that given the two unknowns, I isolate the one I don't want in one of these equations, and then I get what I want. So I've learned over the years that, oh look, and this is what I learned to do as a teacher, and that is, what is the velocity of the 2 kilograms? So I put a circle around that, because that's what I'm after. And so what I learned to do is I say, okay, I'm going to try and solve for V4 in one of these equations, then substitute back in. So if I look here, I'm going to say V4 final is equal to 8 plus V2 final. So there's my rearrangement. And then effectively I take that and I put it in here. No space, so I'm going to come back around here. So I'm going to say minus 2 equals 2V2 final plus 4. And rather than V4 final, I'm going to put 8 plus V2 final. So I just substituted that 8 plus V2 final in for the V4 final in there. So now let's expand that. Minus 2 is equal to 2 V2 final plus 4 8s are 32. I'm sorry. Yeah, I got my equal sign installed, yeah. Plus 4V2 final. And then let's rearrange. So let's click that. Let's take the 32 to the other side. That's minus 34 is equal to 6 V2 final. So then I come along here and I go, oh yeah, V2 final is equal to minus 34 over 6, which equals 5.66, and it's a negative 5.66 meters per second, and it's there. And it's there. It's much easier, much easier doing it that way than it is doing a half mv1 initial squared plus a half mv2 initial squared and so on. You can try it, just try it sometime, and it's like you'll be going through paper like crazy. So this little expression, the difference in the velocities before is equal to the minus of the difference in the velocities afterwards is a real help. It's so useful. So, although the principle is conservation of momentum and conservation of kinetic energy, we use that little cheat to get the... and if you don't like using cheats like that, then try it the long way, and pretty soon you'll realize that the cheat's there for a reason. It just saves you so much time. Cool? So, elastic collision. We can do some of this with IJK, which is kind of nice. 4 kilogram particle. And it doesn't matter which direction you do these in, it's just symbolic. 2I plus 3J plus 4K meters per second. Collides with a 2 kilogram particle. Let's have a 2 kilogram particle. Let's say that's going up like that. Oh, really? I should have them. They're going to miss like that. So I should have them trying to reach each other. So goes like that, and that's going to be a 2I minus 4J plus 2K meters per second. And what is the energy, the combined mass after a perfectly inelastic collision? Oh, again, I'm double telling you. I could have said, what's the velocity, what is the velocity of the combined mass? Then you go, oh, combined mass means it must be a perfectly inelastic collision. So I don't have to say this after. So there's my V. So there's my visualization. So let's have a look. P initial equals P final. So I'm going to say it's going to be 4 times, it's just an IJK. Added to equals so I don't mind. I'm not going to kind of cram everything in horizontally. If I'm not going to fit, I'm going to just put them vertically and just put a plus sign there with that little bracket. They combine afterwards, so the total mass is 6. So let's just multiply this out. This is going to be 8I plus 12J plus 16K. Most common mistake on something like this is they'll do the first, they'll do 4 times 2, and then they're off just not multiplying out the others. But the 4 multiplies throughout. It's literally 4 of these guys added together. So you've got to add all the I's, you've got to add all the J's, you've got to add all the K's. And this is going to be 4I minus 8J plus 4K. And that equals 6V. So now I can add these together and say, well, that means that 12I, 12 and 8 plus 4J, 16 and 4 plus 20K is equal to 6V. So now you just rearrange. V is equal to 6 over, it's going to be 2I plus, this is going to be 4 over 6, 0.67 it should be, J. and then plus 20 over 6, 3.33k. Again, most common mistake now is people said, I'll put all those letters down. I don't need to put my units down, but you do need to put your units down. Little hats on these unit vectors to make them look nice. And there's my answer. So it's going to be 2.66 and 3.75. Oh, there we go. Yes, that guy. Cool. Not bad. Yeah. So I can dress it up a bit with an IJK. I wouldn't do that with an elastic one, that's for sure. You know, I'll do it with this. I'll do it with just the inelastic. That's fair game. But elastic collision, I wouldn't go near it on this. Cool. So there's collisions. You're going to get a question on collisions. You know it. You're going to get an impulse momentum type thing. You know, momentum I'm going to test you on probably with the collisions, but there could be a conceptual question or something like that. Don't not get the easy stuff because you're just focused on the set piece questions. Study the easy stuff as well, so that if I ask you an easy question, you're not giving points away because you're not ready for it. But you know, there's going to be something on impulse momentum, and there's going to be something on collisions. I can guarantee it. So then we have a little bit of a change of heart. This could be the beginning of the next chapter. In different books, it's an orphan. They don't know where to put it, so it moves around. Okay, we're going to do it here. And there's some set pieces here. Okay, and we're going to get to the triangle. That's the name of the game. And I'll tell you now, the triangle is going to be on your test because it's one of those things where I want you to master this technique, and I will pay you to master the technique. I'll tell you this type of question is going to be on the test. I'm going to assure you of it. I want to see it done properly. If you do it properly, I'll give you the point for it. If you don't do it properly, you finagle it, then you won't get the point for it. But this is, for a certainty, is going to be on the test, and it's going to be changed remarkably little. I'm going to change the numbers. And there could be a little bit on these first two steps as well. So if I take something, it has a balance point, or if I hang it via a string, it will tend to find its position it wants to be in, depending upon the way it is. Yeah, I can wiggle it and it kind of goes back. So there's something lining up here, and what we say is it's the center of mass. The center of mass is hanging underneath the hinge, the pivot point. Or if it's balanced, you're balanced when your center of mass is above, you know, the base. What's not so clear is if I throw something, it will tend to spin about the center of mass. You can't throw something and have it spin around the edge unless the edge is so heavy that is the center of mass. I remember when I was a kid, sort of some of my richer friends went to Spain for their vacation, and they came back with all these stories about in Spain, and they made it sound like everybody in Spain had a throwing knife that could kill you at 50 paces, and it was perfectly balanced, so no matter what they did, the blade always came first. You know, it's like magic, and they probably, you know, they might have because Spain has a lot of Toledo steel, so I think they walked past a steel, you know, shop, a lot of knives where they make steel, and you know, you take them home as souvenirs, and you know, then people started talking, oh, that's a throwing knife and all that kind of stuff. But anyway, so as a physicist, I know the way things are, the way things rotate is all about the center of mass. We want to go into this next section, next chapter, which is all about center of mass. So which is all about rotation. So we need to be able to find out where the center of mass is. So we need to develop some of these skills. And so the first thing we're going to look at is just two particles on an axis, just like, you know, Nothing in between, just a particle here, particle there. So we say we have a little particle, which is m1, and we have a bigger particle, which is m2. And I'm measuring them from some reference point, maybe the origin. And I say, well, little m1 is x1 away, and little m2 is x2 away. And the center of mass is given by, and it's just this. The center of mass is equal to the sum for each particle, its mass times its position, divided by the sum of all the masses. So we'll do some examples of that. And then we say, well, that's because it's on one axis. Supposing that we have something that's three-dimensional. I have a particle here in my IJK space, and I have another particle that's over there in my IJK space. Can I do it with IJKs? And the answer is yes, I can. It's the same equation, really, isn't it? It's the sum of each mass times, not its position along the x-axis, but its IJK vector, displacement vector from the origin, divided by the sum of all the masses. So these guys are really the same equation. They're just dressed up. We use r's rather than x's because, you know, we're not necessarily on the x-axis and all that kind of stuff. And then the next thing is we go to, let's say we don't have a couple of masses. Let's say we have a boulder. Where's the center of mass of the boulder? Well, divide it into 1,000,000 masses. Each one has a little bit of mass and a little bit of a distance, so we integrate. So we get our vector to our center of mass. Well, not to say our vector, our distance to our center of mass from this origin point is equal to 1 over the total mass. Well, couldn't I write this and say integral of r dm over the integral, well, the sum of all the m's? Isn't 1 over m, 1 over the total mass, the same as the sum of all the little masses? Isn't it the same thing? And, you know, all right, we had mr and now we have r dm, you know. But can you see how if you know that equation, you can figure that one out. And with a bit of finagling, you can figure that one out. They're not completely unrelated. Just one's the vector form, one's the IJK form, and one's the linear form. But they're really the same equation. I can't justify you why it's RDM and not MDR. And that's my failing. I just don't have a neat justification for you for that. Why not the integral of MDR? And it's just not. Okay. So 3 equations. They are related. I don't think of them as being 3 separate equations. They're like the family. It's like, have you ever been and seen a family of people at one of those holiday resorts together, and they all look incredibly similar? It's like you see like it's like a cookie cutter, slight variations. There's always like I always get a weird feeling about it. And you know, I don't notice it with my family, but I'm sure I've had people. I've had people turn around when my brother and I are not hanging around together much because he's like 5,000 miles away. But you know, I've had people come up to us in restaurants and say, "You two are brothers." Like, you know, oh, we didn't know. You know, it's like because they see that genetic similarity. Not exactly the same, but related. That's what I see here. There's this genetic similarity here. So, a little box at the bottom. For symmetric objects, the center of mass lies on an axis of symmetry and on any plane of symmetry. I don't even follow that, so I'll get to that in a minute. Okay, so let's think about this. So we have a 2 kilogram mass located at position x equals 5. So we're doing it on the x-axis. I could do it on the y-axis, could do it on the z-axis. So this is plus 5, and I'm going to put my mass here, and that's 2. And then a 3 kilogram mass is located at plus 4, so here's my plus 4. And my mass there is 3, it's 3, okay? And I'm measuring from, you know, here, and I'm measuring from there. So I'm measuring from this point here. What I say is that the x position of my center of mass, not centimeters. And I've been teaching this for like, oh, I don't know how many years, maybe 20 years. And one of my students last time said, well, why is it in centimeters? And it never dawned on me that that could be in the least bit confusing. But you look at it and, yeah, cm, centimeters, yeah? We drive it into that centimeters, but in this case it means center of mass. Really I should put down COM, center of mass. Just shows how, with the best intentions, shorthand requires familiarity. It's not like saying things longhand, and so you've got to spend some time making sure you really understand what everything stands for, and not just assuming I can figure it out on the day. So x center of mass is equal to, and it was the sum of, oh, I know what to do. I can help myself in time. I'm going to put down the sum of each x times each m, where I is a number that goes from 0 to however, from 1 to however many little points I have over the center of. Do you see what I've done there? It's like cunning. What did I do that's different from there? Look at that first equation. Which order did the two letters come in? I switched the order. And why did I switch the order? Look at your last equation. Look at the integral. Yeah? So if I learn it's xm and I learn it's rm, then when I do my integral it's going to be r delta m. Just cleaning, it's like combing your hair. It's like if you only do it every now and then it really hurts, but if you just bit by bit just get the pattern, life gets simpler. There's no reason why it tends to be written down this way apart from historically that's the way it's done, and the guy writing the book doesn't even think there's a problem with that order. Doesn't even remember that when he first started or when she first started that they sometimes would get these things backwards, you know. But we can sort that out for ourselves. Just change the order. You know. So we're going to say, okay, so this is, I've only got two of these things, so it's the first one, which is 3 times its distance. I did it the wrong way now. So it's 4 times its mass, which is that, plus, as a sum, it's going to be 5 times its distance from its mass, and it's pretty well ingrained in me, and then it's going to be the first mass plus the second mass. So my xCOM is equal to 12 plus 10 over 5, which equals 22 over 5, which equals 4.4 meters. It's that. So it's applying the system. Think of as a teacher. Think as a teacher. How can I make this a bit more interesting? You know, I could add more masses, but it's just doing more of the same. It's just burning time. So, you know. The way that I could make this more interesting is I don't tell you where the starting point is. I say, that's 3, and that's 2. And I say the distance between them is 1. So now I've not given you an official starting point. Let's see if I can still do it. So I go my xCOM is equal to, every time I write it down it gets a little bit more ingrained, which equals, well, it's going to be 0 times 3 plus going to be 1 times 2 over, it's going to be 3 plus 2. So this is equal nothing plus 2, 2 over 5, which is 0.4. It's not the same numerical answer, but can you see I'm 0.4 from there, which is the same as being 4.4 from there. So this 4.4 is measured from over here, and that's where your 4 is, and then you have your 0.4 there. Same answer. So that would be, I'm throwing you a bit of a curve there by not telling you the starting point. If you want, you could say, oh, I'm going to, in that case, if you didn't tell me, I'm going to just go 1 away. So I'm going to call that 1, and 1, I'm going to call that 1 plus 2. And it'll still work. It's just now I'm measuring from here. Now, what I got to do is I got to give you some measuring point. I say, where is the center of mass? Not particularly well said, actually. I would say, where on the x-axis is the center of mass? So you know you're starting from 0. In this question here, I'd say, where, how far away from the 3 kilogram mass is the center of mass? Yeah.
Well, it's just the address. It's just the address of the system itself, but then your perspective on the system, whether you're farther away from it or closer to it. It's all the same address.
It's all the same?
It's all the same address inside.
Yes, yes. It's consistent within it, but yes. So I got to be a bit careful about how I express it. You know, what length measurement do I want? But it will work. I can do the same thing now. Let's do it using IJK. So now I have a 2 kilogram mass, and this is at 3I plus 4J plus 2K meters. And I have a 3 kilogram mass, and this is minus 2I plus 3J minus 0.5K meters. And I say, well, in this case then, my vector to my center of mass, maybe I should do that, is equal to, well, it's going to be the sum of each vector times each mass over the sum of each mass. So I say, okay, let's do IJK on this. Do a little grid for ourselves.
What's your K component of the 3 kilogram mass?
K component of the 3 kilogram mass is IJK. Minus 2. I got minus 0.5, didn't I? Have I got these the right way around? Where did that 0.5 come from? Oh, because I looked there. Yeah, I looked at the answers. Thanks for catching me on that, because that would have been a bit of a mess. So minus 2, 3, minus 2, and 3, 4, 2. Yeah. Okay. So then I go, well, I want R times this mass. So it's the 2 times that. That would be 6, 8, 4. This is 2 times 3I plus 4J plus 2K. And the next one I'm going to do is I'm going to do that guy, and that would be minus 6 plus 6, no, plus 9, and minus 6. That is 3 times minus 2I plus 3J minus 2K. So 6, 8, 4, 6, 8, 4, minus 6, plus 9, minus 6. Add them together, I'm going to get 0I plus 17J minus 2K and that's the sum, and then I've got to divide that by the sum of the masses, which is 2 plus 3. So my answer is 0I plus 17 over 5 is going to be 3.4 minus 2 over 5, 0.4. Okay. Now, this is going to be a position, so it's in meters. And so it was 0, 3.4 minus 0, 3.4, it's the bottom one, isn't it? Yeah. Cool. So again, it's the same problem, it's just dressed up a little bit different. Yeah. So this is central mass using calculus, and there's two versions of this. There's a rod. I suppose. Well, no. I'm going to show you this because it helps you with the next one. Okay. So there's a rod, a 4 meter long rod. It's positioned with one end at the origin, so there's my origin, and the other end at +4, so this is 0 and that's +4. Uniform, and has a mass, big M is equal to 8 kilograms. Using the method of calculus in physics class, what is the location of the center of mass? You've got to prove it's at 2. We know it's at 2. We know it. It's balancing at 2. You know that, yeah? It's a uniform rod. But let's just prove it to ourselves. So the way we do it is... Nah, that didn't work. We imagine a little slice. And the first thing I say is I say my center of mass is equal to, what was it? It was the integral of RdM over the total mass. Yep, that was my equation for it. And the problem is we don't know how to integrate R with respect to dm. There's my dm, and here's my dr. And if I could somehow express this dm in terms of dr, I could integrate it. So what I say is express dr by, and you're going to use some physics, and you're going to say dm is equal to dr times the linear mass density. Now you know about density, it's mass divided by volume. But if something's uniform like a rod, you could talk about the linear mass density. It's the mass per unit length, you know? So dm is equal to, well, the longer the dr, the more mass I have, so dr's I just multiply by. And then the linear mass density will be the total mass over the total length. Because it's uniform. So this equals m over L dr. So that's a little bit of an aside. If you want to check it, use symmetries. The little bit of mass over the total mass is like the little bit of length over the total length. So let's just start off here. The little bit of mass over the total mass is equal to the little bit of length over the total length. And if you rearrange that to get dm, dm is equal to m over l dr. Isn't it the same? So if you want to just check it. I mean, the physics is you take the little bit of length and multiply it by the linear mass density. And I want you to learn it that way because later on we're going to do problems where we need the area mass density and we're going to do some problems where we need the volume mass density. So there's a pattern here. Sorry, let me stop that. How long have I got? I've got 10 minutes. I'll be all right, yeah. So then all I do is I say, okay, so now substitute that up here. And I'm going to say, well, R center of mass is equal to the integral of R. And rather than dm, I'm going to put down m over L dr, all divided by m. And this equals, let's take out our constants. It's m over L divided by m, the integral of R dr. Just rearrange it, yeah? Simplify. Center of mass is equal to 1 over L, the integral of R dr. And to keep in letters from 0 to L, because that's where I'm going, yeah? From 0 to L. So this would give me 1 over L. Let's have a look. Increase the power by 1 and put it in the denominator. R squared over 2 from 0 to L. So R center of mass is equal to, well, let's have a look at that. 1 over L. L squared over 2 minus 0 squared over 2. Our center of mass is equal to L squared over L times 2, which equals L over 2, which in this case is equal to 4 over 2, which equals 2 meters. When I was a student, I felt a desire to get to numbers as quickly as possible. And I understand that. And there's nothing wrong with substituting numbers in earlier. And it always frustrated me. Why are they doing this? Why are they leaving the letters in until the last minute and then shoving the letters in? And there's two reasons for that. One is, when you shove numbers in, especially if you then divide numbers out or multiply numbers out before the end, when you combine numbers like that, you've combined parameters. And so checking it visually at the end is harder. Because what does that 6 mean? Well, it was a 3 times a 2. Oh, yeah, okay. But it's a 6 now. Could have been a 12 divided by a 2. It's like, you know, when you combine numbers, you forget where they come from. If you left the numbers in and just didn't do any math on them, you know, didn't multiply or divide them, so they were still there at the end and then did all the math, that would be a bit more straightforward. But when people substitute numbers in, they tend to cancel out as quickly as possible. It just makes checking up harder. So by leaving letters in, actually, it's easy to just check the algebra of it, you know. And then at the end, you substitute numbers in. So that's one reason why they do it. It's easy to check. And the second is sometimes you find that you end up with things cancelling out and you realize that physical parameter is not significant. If it's just numbers, you don't get that. But if you find the mass cancels out, I'm not referring to this case, but if you find the mass cancels out, then you go, oh, mass doesn't matter, it's all proportional, and it doesn't matter. So there's some insights come from leaving letters in. I don't care which way you do it. It's like, if I look at this and I see a diagram that makes sense, and I see the equation, and I see this little box here, and I see you substitute in, and you do the integration right, and you have the right limits, and you get the right answer, I'm perfectly happy. It's like, if you just give me the answer, if you say, I did this in my head, no points. If you basically learn that for a straight rod, the center of mass is half the length, no points. It will say, using the method of calculus as shown in physics class, because this is what I want. You know, you don't have to lay it out the way I'm doing, but you got to get those major things. You got to show me the equation. You got to show me the diagram. You got to show me this conversion. You got to show me the integration. You got to show me those bits. Yeah. Cool. What I don't like about this example is that I don't need to put it on the origin, so I can put it here. And then L, so there's my L, but the limits of my integration are not L and 0. They're whatever this happens to be and whatever that happens to be. So down here I'll get a slightly different limits of integration. Okay, there's practice on that on homework. I might, in future, just get rid of... so let's stop here.